Hey everyone, this video is to apply a lot of the little things that you are learning and overlay them with some stats theory that is going to build you to the idea of hypothesis testing in a study. So before we get too far, just a reminder that a statistic is a summary characteristic of a sample. Usually we're talking about a mean or standard deviation, but it is about a sample. A parameter is a characteristic about a population. It can also be a mean, but it is the mean that represents the entire population. When we've been talking about sampling, it's all about probability or non-probability. A probability sample means that you can calculate the chance of being included, and everyone has a chance to be included in the sample. That does not mean everyone has an equal chance, but they have a chance that can be calculated. A non-probability sample means that there is absolutely no chance of being selected and that we are purposefully, typically, selecting certain people. So probability samples are preferred in quantitative studies because it can help us assess precision. We can actually estimate the sample size needed to get a certain level of precision. It helps us reduce sampling error, and it just gives us more confidence in our estimates. So a quick reminder on the concept of distributions. Each one of these pictures is a sample and the distribution of the data in that sample. So here we have some distributions that have similar patterns, and we can see some that look fairly normal. But each one of these is a distribution of a sample. We are now going to talk about a sampling distribution. So a sampling distribution is the distribution of a statistic drawn from all possible samples of size n in the population. What? Read that again. A sampling distribution is the distribution of a statistic drawn from all possible samples of size n in the population. Read it again. Got it? No, of course not. So here's an example. If I want to sample my classroom of 12 with a sample size of 6, so I could sample these 6, 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 but keep in mind that every time I sample them, I'm putting them back for the next sample. So how many combinations of 6 can I have? There's actually 924 different possible combinations of 6 in this classroom. If you don't believe me, there's the website at the bottom. This gets more confusing because what I'm going to do is I'm going to take these 6 that I first draw out, and I'm going to calculate a mean score for them, and I'm going to write that down. I'm going to put them back, and I'm now going to calculate a mean score for these 6 that I drew. I'm going to put them back, I'm going to draw another 6, calculate a mean, draw another 6, calculate a mean, until I have 924 different mean scores. When I look at the distribution of those 924 different mean scores, that is a sampling distribution. So when we're talking about a raw score distribution versus a sampling distribution, we're talking about 6 leaves compared to the entire tree. We're talking about 6 trees that we're using to represent the entire forest, or a drop of water compared to the whole ocean. So a raw score distribution represents a sample, and the sampling distribution represents all possible samples of whatever size you choose that there are in that population. So let's read this again. A sampling distribution is the distribution of a statistic, a mean score in this case, drawn from all possible samples of size n, which was 6 in this case, that there are in the population, a classroom of owls in this case. Good news is we don't actually do this in real life because we have theory, specifically the central limit theorem. This states that sampling distributions of means tend towards a normal shape as sample size increases, as long as it's reasonably large samples and it's randomly selected. Reasonably large means 30 is usually enough. 30 is a magic number that has come from theoretical statisticians. Yes, that's a job. that they did lots of simulations of random data sets, and they determined that if you have 30 cases, you're usually good. And it will follow this distribution of normal. And they noted that as sample size increases, the variance of the sampling distribution decreases. This right here is our argument that yes, 30 is minimum, but we want more. And this makes sense if we think about variance and what it is. So the variance here is basically how close are all these dots to each other. And in this case, they're very spread out because there's not as many of them. We have a lot of white space here. But as we fill that white space with more samples, with more dots, we actually have less variance in this picture than we do in this one. So as sample size increases, the sampling distribution decreases. And we actually apply this, and the number that we can look at is called standard error, which I know that you have seen and heard of. What I want you to know is that smaller is better. It's just hard to say a specific value because it's completely dependent on the data in the study that you have. There is a really good read that I want you to stop and do, which is standard deviation versus standard error, which helps you kind of conceptualize what the heck this is. But basically, we're trying to indicate that the estimates that we are making, the inferences that we are making, are more reliable if we have a smaller standard error. So pause, make sure you can answer these trivia questions before moving on.